So NATs are brilliant. NATs are literally brilliant. And they've kept the internet going for the next 20 years. And they did it so well. Don't lose your eyes on the global endpoint. We're going to be running V6. This is just a short-term expedience. Everyone's going, meh, short-term, I haven't got a problem. And all of a sudden, the short-term became the long-term answer. And here we are with this mythology that we're still transitioning to V6, but we're not really. Some 36% of the world's, 5 billion users, or however many there are, can do V6, but the other 63% cannot. We lost track.
You're listening to Ping, a podcast by APNIC discussing all things related to measuring the internet. I'm your host, George Michelson. This time, I'm talking to Geoff Huston from APNIC Labs again, in his regular monthly spot on Ping. Geoff and I discussed the IPv6 transition, despite some highly significant deployments, like India, which now shows 80% IPv6 capability, following a surge in deployment when Reliance Jio launched an IPv6-based service nationwide, or Vietnam, which is at 60% capability and rising, with a nationally planned and coordinated deployment amongst the competing ISPs. But despite these significant deployments, and others like them, the pace of uptake of IPv6 worldwide has not improved. It's basically linear at 30%. At this rate, a realistic completion date is beyond 2045. Deployment in the USA peaked in 2019 at around 60%. It's been sitting there ever since. This is troubling for proponents of an IPv6 transition. The emerging reality is that we're going to be operating a dual-stack IPv6, IPv4 network for the foreseeable future, probably for the rest of my lifetime, unless something changes. The success of carrier-grade NAT, or CGN, and the shift away from routing as the primary conduit of content delivery to more local connections to content distribution networks has fed a sense in Geoff that addressing in general, and IPv6 in particular, just isn't as relevant to the success of the global internet as we thought. Geoff, welcome back to Ping. What should we talk about this time?
Hi, George. Hi, listeners. I had to do a keynote presentation to the North American Network Operators Group in the sort of middle of October. Unfortunately, I had to do it virtually because I fell off my bike and injured my poor body. But I actually want to talk about what I talked about at NANOG here, because I actually think this is kind of fascinating. And the basic theme of the talk is IPv6.
Oh, my favorite big number network.
That's right. And it's kind of, why hasn't it happened? Why are we in this limbo half-life of bits of the network have got V6, and that's great, but a whole lot of other bits of the network don't?
Now, let's be a little clear here that hasn't happened, in air quotes, means lock, stock and barrel pick up our everyday experience and move it from 4 to 6, just like we did with Novell, Netware and DECnet. We're not in those protocols anymore. Where we are is a little from box A and a little from box B, right? It's not that there is no 6, it's that we haven't decided to complete a path to only being in 6. We're living in both.
Well, the problem is that, and we can go back into why we are here, and maybe it's worth doing that, they're not compatible with each other. You speak 32-bit V4, I speak 128-bit V6. If that's all either of us spoke, we cannot communicate with each other.
So at that level, it kind of fundamentally would break an ability to perform operations between you and me unmediated. So right out of the door, it's like we've made a decision here that defeats the purpose of ubiquitous internet. It ain't ubiquitous anymore.
So I'm going to wind the clock back, step into the TARDIS, into the time machine, whir, clunk, woo, 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 strange noises, and actually come back into, what are we talking about here? What's this V4, V6, 32-bit, blah, blah, blah? What's the background? And then I want to sort of move it forward to understand why the world doesn't operate according to the rules that the technologists set out for them. They've gone off-piste. They've left the reservation and they're out in nowhere land, and we don't understand anymore. So let's go back to 1988. Was that a good year?
That was a pretty good year. That's when I came to Australia. I love that year.
Well, there you go. Great year. And the early internet was gathering momentum. Now, at that time, IP was a remarkable protocol. And I've got to put it in contrast what else was around at that time. And one of the dominant ones on the university campuses was DECnet, and had just gone from phase 3 to phase 4. Now, DECnet had 16 bits of addressing, which meant you could number machine number 1, number 2, all the way up to machine number 65,536. That's a lot of machines. And I remember going to a presentation from Digital around that era where they proudly boasted at the time that they'd sold their 100,000th VAX machine. And so the scale of the DECnet network and the scale of computers at that time were actually on a par. 65,000.
Yeah, it was broadly speaking a good fit for the circumstance. We touched on this the last time we talked about 240/4 and the scale of networking that was envisaged at the time. And so DECnet Phase 4 was kind of an interesting place to be because it was actually a structured network. It had an idea there would be areas and that there would be a local component, and they were trying to construct a world that would have a concept of routing, but it was fundamentally based on some numbers that I think even then were challenging for the size of industry, research, the community at large. But nonetheless, 16 bits of address, 65,000 hosts, good fit for the size of a campus then.
That's right. They didn't have dreams of global domination. So you didn't coordinate your DECnet addresses with your neighbor over the road, with any other university, with anything. Everyone started off naming the first VAC DEC machine Area 1, Node 1. And the next one was Area 1, Node 2. We weren't trying uniqueness. The internet was something different because even in the mid-80s, as we started to deploy these machines running this weird IP, you could invent an address. And a lot of folks started off using Network 10 because that was the only thing they'd read. But you could also send a fax. Remember that?
Oh, I sent those faxes where you declared how many you had, how many you thought you'd have in 5 years, and the crucial question, do you intend connecting to a globally connected internet?
Do I intend? Of course, I have every good intention. And they would come back going, here, have a Class B network. And it would need a bit more negotiation. I'm a very big campus. I'm like MIT. And you wrote to John Postel, John would go, oh, yeah, well, we'll give you an even bigger block of addresses. We'll give you a Class A. And I don't know why you'd ever ask for a tiny block, Class C, but most folk just asked for a B and got a B. Now, what that meant was that a whole bunch of folk in the 80s was sending their faxes off to the IPNIC and getting back a bunch of addresses. And what they'd done is they'd divided up the 32-bit address space. One half was reserved for humongously big networks. It managed to do 126 networks, each of which could have 17 million, just under 17 million computers connected in their network. No one ever did, of course. And around about a quarter of the address space was a bunch of addresses, 65,000 Class Bs, each of which could accommodate 16 bits of hosts, 65,000 hosts, which for campuses was kind of perfect. Workstations were coming, personal computers.
So in that model of addressing, given DECnet stood up and said we can handle an area having 16 bits of host field, this was in some senses, we've got that. But unlike DECnet, there was no ad hoc area coding. You were given a unique identity for the equivalent in internet terms of your area. Should you ever globally connect, you were not going to collide with well-behaved other people who weren't just randomly grabbing an address. So this was quite an attractive scheme. This is the benefit of a registry.
Well, it was, but I must admit, speaking as someone in the lower antipodes in the mid-80s, ticking a box that says, we intend to the internet, caused some polite laughter inside the computer center where we were going, bullshit, never going to happen. Can't afford it. This is just pie in the sky stuff. But we'll tick the box. We'll get a unique, the equivalent of an area number, a network number, and off we go. Problem was, how many universities in the world are there?
Oh, gee.
Tens of thousands.
It's 20s of thousands. At the time I left the UK, there were 200 in the UK alone, and that was before they folded the colleges of further education into university status. So the university system was exploding worldwide.
Right. And if you then look at the companies who had computers and and then you observed that in this increasing multi-vendor world, the only technology that straddled all the various vendors was IP. If you bought a digital machine and you ran DECnet, you looked at all your Wang word processors going, well, I guess you're just out of luck, everyone. Anyone who was sort of buying bits and pieces, as a lot of companies did at the time in the 80s, found that networking was a nightmare because all the networks were corporate. They were all tied to the mainframe. IP was the key to get you out of vendor jail. And the other part was, thanks to a remarkably prescient contract that the folk at DARPA did with the University of California, Berkeley produced an implementation of TCP/IP and made the source code available and royalty-free. So not only was this source code runnable anywhere, and it did, you didn't have to pay anyone. So between those two, open and free, how seductive, all of a sudden the industry went, problem solved. I don't need to build my own vendor proprietary networking stack. IP will glue this all up. And so even in the world of the late 1980s, when it was still mainframe dominated, IP was exploding.
And exploding kind of carries with it the seeds of its own destruction, doesn't it?
Well, it does. And a gentleman by the name of Frank Solinsky, hi Frank if you're listening, appeared at an IETF, an Internet Engineering Task Force meeting in August 1990. I think it was Seattle, could have been Vancouver. It was up there on the West Coast, who said, hello, fellow geeks. It's now August 1990. We're going to run out of Class B networks in March 1994. Everyone's kind of go, what?
Oops.
Here's the maths to prove it. Oh, God, you're doing maths. Damn it.
Yeah.
And he was right. All of a sudden, this internet, which we'd been evangelizing, saying it's the answer, it's better than anything else out there. Even the telephone companies and government efforts with open systems computing. No, this internet stuff was practical, really dirt cheap, and it worked. And Frank's going, nah, it's got no future.
So the open systems interconnect people, which are worthy of derision, Geoff, I was one and I will accept the burden, did at least at that time have a sense that the number field for addresses was going to have to be larger. So as a theoretical network, and let's be clear, there were research implementations, no deployed connectivity globally, no actual sense of structural adoption, but at least in their design thinking, they were trying to head to 32 bits may not be enough. So Frank standing up and saying, here we are in a 32-bit world, and I can tell you it's not enough. There were other people saying, we think that might have been the case, and we've been building a belief it's going to have to be a lot bigger.
At the time, I'm sort of deriving this from indirect stats, the telephone network spanned around 500 million global subscribers. And if you're coming from that space and you have this wild, crazy dream about data networking everywhere, big numbers of the order of 1 billion weren't silly. They were conceivable.
Yeah.
And yes, the OSI folk did indeed have a much bigger dream. And I suppose it wasn't really that the internet's dream was any smaller. 32 bits was considered insanely big. 4 billion was a lot, but almost on day one, they carved it up.
Yeah.
They carved it up into this part is a fixed network identifier, this part is a fixed host identifier. 2 by 16 bits was the most popular. We weren't going to run out of addresses. We were going to run out of Class Bs.
Yeah.
We were going to run out of that quarter of the space that we'd carved in a certain way.
Yeah. So as we talked about in the 240 ping episode, it really means you've got to divide the problem in two. And one of them is the work that Frank initiates and the conversation has to lead to, can we have a more nuanced sense of how big the boundaries are between an area and a block of addresses? And the other is we need a long-term solution.
And the folk going to the IETF at that time and the industry participants weren't stupid. And they did devise the short-term hack, the long-term long answer. Because if we got rid of the class structure, just got rid of it and said, 16 bits for your 40 computers on your local network, 16 bits, 65,000 is kind of overkill. If you've got less than 64 machines, you need less than 8 bits to number them. So why don't I just give you 8 bits, and so on. So why don't we get rid of the fixed class structure, which is just so inefficient, and get back to something that kind of is variable? Now, the internet folk went, that's a lot of work. We're on a fixed term government contract. And the answer really was the internet, fine, we'll get a whole bunch of people doing this work. And in fact, we'll set up some regional registries and we'll get folk to do the address administration, which is now a lot harder, and do it all around the world. And so before you knew it, the Americans had one, the Europeans had one, Asia Pacific had one, which we work for APNIC. We were off and running in the short-term hack.
So if you put yourself back in the headspace at the time and you'd said to someone over a beer at the bar, how long do you think this short-term hack is going to buy us? Well, you've said a thing to me in other contexts. Nobody can tell the future better than 5 years out. And frankly, even 5's a bit of a gamble. So anyone saying they think we've got a 10-year window here or a 12-year or a 15-year roadmap, they got rocks in their head because nobody knows what the future's going to look like. But we'd all have kind of said, oh yeah, we'll get 5 out of this. And we'd also, because we were young and naive, we'd have said 5 years to fix the problem for the long term, easy peasy. We'll be out of this problem in no time at all. I am confident we would have said we don't need to do it for long and it's going to be a better world.
Well, that was the whole idea. Yes, the issue behind this was the personal computer revolution by the late 80s, by 1990, was absolutely underway. IBM PC first came out in about 81, 82. And so they were selling personal computers as consumer items. And while the internet at home was considered a bit weird, it didn't take much imagination to dream of it. And so you could conceive, even before mobile phones, that 32 bits wasn't enough. Now, you might have said, oh, it'll take us 20 years. And some of the optimists would say, no, be quicker than that. But whatever you sort of thought about, it was within your lifetime. It was within planning range. And if you're going, shall we invest a massive communications enterprise in IP on the 32-bit addressing structure, the answer would be, you're crazy. We can't do that. And so the long-term folk at the IETF said, must have the long solution. And across about a 4-year period, there was a lot of angst, thrashing and dreaming in the IETF about what does it look like. There was a crowd that said, if IP was just an experiment, and it was just temporary, and it was, let's use that learning to make what the phone companies doing better. Let's make the OSI protocol suite sort of learn from this and adapt. Now, at this point, I think some rather messy transatlantic politics got in the way because over in telephone land, the North Americans had been fighting with the Europeans over digitization of the telephone network like crazy. Why is ATM a camel where the payload's 48-bit? There's sort of 7 bits of header. What's this 53 bytes of ATM? And the answer was French versus American.
And that battle of Europe versus America reached out into things like the ITAR regulations on the traffic of cryptography, sale of telephone equipment to Eastern Bloc economies. It wasn't just a protocol war about 48 versus 56 bits or 1.44 meg versus 2 meg. It was about which companies are going to secure large-scale contracts to sell equipment. It was a trade war.
There was money, not principle. So even though the Americans used A-law digitization and I think the Europeans used mu-law, everything was different because the giants in Europe, the Siemens, the Nokias, etc., I'm not sure if Nokia was a giant by then, but the giants in telecommunications in Europe were unable to penetrate the US market. And the giants in the US were unable to penetrate Europe because they'd put all these technical barriers up. That wasn't the same technology. And so when IP was kind of going, well, shall we move on to OSI? There was a certain gut feeling in the Americans going, what, give up and surrender our entire sort of enterprise of digital communications to the Europeans? No.
Yeah.
And it wasn't even sort of, well, invented here, it's obviously better. It was kind of, we're talking the global communications enterprise. This is not going to be handed over easily. So at the same time as some folk were saying, let's rebuild the internet in the guise of OSI, a very strong and determined voice was also saying, that's just political nonsense. Let's just make IP better. Let's future-proof it.
So an underlying point here is that even inside a domestic economy at the scale of the USA, federal state agencies were getting aware that they were going to need a globally connected framework. They may not all yet have understood it was going to be global into the public space and not just FedNet, but they already knew they were talking about connecting a large number of entities. They kind of wanted a solution that was good for them alongside this economic question. Is it good for Europe? Is it good for the world? What's the trade positioning? They wanted a real problem solved.
And indeed, government sponsored across a lot of the developed world this thing that you probably will know and some listeners might fondly recall, gossip, the government OSI profile. And the whole idea was, if you can align your supply channels to build OSI solutions, because OSI was kind of so amorphous, It didn't guarantee interoperability. You had to pick a profile.
Yeah, you had to narrow the scope of this standard soup down to a much thinner conformance. But the good put here would be I could slap a tender on the table and say, I'm buying 50,000 endpoints. This is the profile I'm aligning to. Give me a quote. And it was no longer a battle over what's in and out. That was the dream. Simpler bidding, simpler quoting, simpler RFP.
It was the dream. Over in the IETF land, these bunch of liberal lefty geeks wearing T-shirts and shorts and long hair and beards were wandering around going, bullshit. We don't need no paperware about vaporware. Our RFCs are based on running implemented code. If you say to a vendor, RFC 1090, and someone else says the same RFC to a different vendor, they will interoperate. They will. And indeed, the entire sort of tenor at the time was expressed in these things called the Interop Conference, where once a year, a whole bunch of folk came originally to San Jose and overnight built this massive network inside the convention center. All the vendors came along and the network worked.
Yep.
They bought their equipment and it just worked.
So we didn't have blogs in those days because this was a little pre-web, but there was a component here that the people who had to build that network actually were sending out emails to a community and news posts on things like Usenet News saying, if you've never helped build the shownet for an interop, you might be interested what we actually have to do to make this work. And it was fascinating, the kind of ways that they were constructing a viable network ad hoc in about a day and a half to 2 days for everyone to get together and do a test like this. It was somewhat challenging.
So IPv4 won on the interoperability, practical, cheap, working model. OSI was none of that.
No.
None of that. But the problem with IP was, by 1990, it was true to say, it has no future.
Yeah.
The computing industry is going to walk all over us. We're not big enough. So the long-term answer was, what do we do? Lots of ideas came in the door, and there were kind of two answers. One, dream, go crazy, do weird stuff. And the other dream was, why don't we take the existing IPv4.c or IP.c and replace the constant 32 with a new constant, 128, and recompile the code. Change almost nothing, just bigger address fields. And because this was an address-based network, if you did that, you could accommodate not another 4 billion, you could accommodate 2 to the power 128.
Yeah.
I'm not going to bother figure out what the nomenclature in English is. Just let's say, even if a grain of sand, if you used a whole bunch of them to build something the size of planet Earth, you're still below 2 to the 128.
Yeah. If you think back to the mailing lists that were discussing why would we want to do this, there were people there who were working in tactical network design for NATO. And they had come up with a model that was effectively about command and control logic for the battlefield, where a person had to be capable of being picked up, put in a helicopter, flown to a location, dropped on the ground, and come into being in a connected network with the chain of command. And so they already had a magic 48-bit number that was the NATO ID of that individual. And they were looking at this large address field saying, are we going to be able to construct routing models where the identity of the NATO person embeds in the address field? And looking at 128 bits, it was going to be perfectly possible for them to do it. Now, of course, many people were saying, that's not the internet. Many people were saying that's got nothing to do with how you or I are going to construct static networks based on our location using the internet to do ordinary things. But the point here was the model of internet protocol was going to work in contexts that were completely different to things we were used to doing.
Right. So the thinking behind the technology in designing the next IP, and they did a whole bunch of white papers, was this protocol will work for everything we can dream about. They asked the power industry. They asked the consumer device industry. They asked the military. They asked a whole bunch of folk going, how big are your dreams? And that's how they kind of justified this quite extraordinary lift in the address space to impossibly big numbers.
Yeah.
Now, designing V6, once you'd made that decision, was actually really, really easy because almost nothing else changed. Almost. There are only two things that really changed. Both of them were bad that we changed it.
Yes.
One, fragmentation.
Yep.
Geoff Mogul, working at DEC Western Research Labs, has just written a paper basically going, packet fragmentation on the fly is impossibly bad. It's a security nightmare. It's just evil. And the designers of V6 said, okay, fine, let's get rid of fragmentation on the fly. It was in the early draft, and then all of a sudden it disappeared. Oops.
We've talked about that on Ping 2, and it's one of those moments gone by that we're just going to have to live with.
Unfortunately, but that was problem in the left heel. In the right Achilles heel was replacing the address resolution protocol with multicast. And I think the only reason why we made that misstep was that Steve Deering's PhD was in multicast, and he was one of the two designers. It's kind of, here you are, Steve, have your dream. We'll do it with multicast. Yeah, great. Anyway, most of the rest of us kind of mostly worked. And the theory was, well, there's two things going on at once. The short-term answer was never meant to be a long-term position. It was just a Band-Aid to let us finish the V6 work. But once we'd finished the V6 work, we were going to rip the Band-Aid off. We were going to stop this short-term stuff and get back into where we were with 128-bit addresses, right?
Yeah. So it was absolutely a move over there moment. The headspace, the way we were thinking is there'll be a process and then, well, we don't like flag days and we can talk about that. But the vision is I'll be driving a shiny new car on a bigger highway over there. I'm not on this road anymore.
No one's in charge. No one's calling the shots. No flag day. So why are people going to make the move? And the answer is, if the short-term expediency doesn't last very long, you got to make the move. You're forced. There's no choice. Except,
here we are. What year is it, Geoff? It's 2024. And how many people have decided to get away from this terrible world of IPv4 because it just isn't there anymore?
NATs are brilliant.
Yeah, NATs.
Network address translation, sharing addresses. NATs were stunning. Not only were they technologically stunning, it was kind of business stunning in the same way that I think BGP was a natural fit to the way we did routing at the time in a business sense. NATs were actually a natural fit to the way the emerging IT industry was kind of looking at this. You see, not everyone should be able to publish content. Not everyone's a server. Not everyone is able to, if you will, broadcast to everyone else. That's just chaos. So let's divide the world up into clients and servers. And let's make sure that clients sit at the back and consume content but can never publish under their own steam. And let's choke the publication channels and make them all into big machines run professionally in data centers as servers.
Yes, the emerging reality that suited intellectual property, the money interests, the entertainment sector, and virtually everyone looking to actually scale out and build, but which wasn't really what we thought internet was about.
Well, you see, some things happened even at the technology level. The telephone system was built symmetrically. You're talking, depending on the encoding, you either consume 56 kilobits per second or 64. I'm talking, same bandwidth. So the bandwidth between us, the requirements are symmetric. I don't need to provision 8 megs down and 1 meg up or anything like that because it's just people talking. But in the server client world, clients are consumers.
Yeah.
So they're not allowed.
Clients are a bit more like me. They sit here going, yep,
yep,
yep, yep,
yep,
yep.
Low bandwidth.
Lower bandwidth.
And oddly enough, it was almost by a happy accident, this suited the modem folk who were trying to make the telephone network handle more data. It's really, really hard to push large volumes of data over complex encodings back up through the twisted wire copper network. Because when all those signals get close to the central office and are concentrated together, that's massive crosstalk. You can't make it fly.
Yeah.
On the other hand, pushing it down allows you to actually run with quite a high power budget because immediately all the pairs split out through the distribution network.
Yes.
And so it was quite possible to build modems in the end. We got up to 56 kilobits per second down, but you never had that coming back up. It was all asymmetric.
Yeah.
Because you couldn't make it work any other way. So it's kind of suited the technology of dial-up and the business model that says, pay us money to be a server. If you're a client, oh, that's easy. We can make that happen. And so all of a sudden the network became asymmetric. And NATs slotted into that model. And it was like a hand in a glove. It was perfect. Now, NATs gave you another 16 bits of port space because it invaded the next level up, the transport layer, and said, clients don't need permanent addresses. They just reach into the pool and grab one.
So we're making a kind of inferential jump over the concepts of layering here, the point being that the unique identity of what you are in a conversation with another party isn't only about the pure IP layer of your host address. It's a function of your host address, the specific protocol above IP you're using, in the IP layering model within that protocol, a port number, and then further inside a computer, a magic number we can call effectively the process ID. If you string all of those together between me as a user and you as a user, you get this thing we call the 5-tuple. And that 5-tuple has a lot more bits, air quote, in it than just the 32-bit address. As you said, 16 bits of port address magically glue into the network.
Now, let's go one bit further here. I can take my personal computer with a TCP IP stack connected into a network with its own unique public address. And I can unplug it, take it home, plug it into my home network, which sits behind this dial-up modem NAT gateway. And instead of having a permanent address, it gets given an address from the NAT gateway. And it's the NAT gateway, whenever it tries to make an external communication, basically sets it up with a dynamically assigned part of that IP address, a new port number. My machine doesn't know it's behind the NAT. Nothing changes. So all of the end host software never had to do a thing. The server doesn't have to change, didn't do a thing. NATs were this sort of pinpoint change that had this dramatic implication on the efficiency of addressing, but didn't require everyone else to reprogram.
So there were a few complications. I mean, you are gilding the lily a little, because if we go back into those days, designers of protocols, applications expecting to connect to a server had made some simplifications in their coding that assumed they wouldn't have to ask the critical question, who am I? That it was implicit their IP address alone would be enough to say, this is who I am. And so intruding into the conversation when NATs emerged was two problems. One is you can't know from inside the NAT what you look like on the outside. And the second is there may not only be one NAT in the way, there could be 2 or 3 or 4 or more. So
Yep.
nothing in the host had to change, nothing in the IP stack had to change, nothing in the global routing model had to change, but the application developers had to work a little harder.
Oh, not much, George, because don't forget two-party models. Hi, I want content. Yes, here's content. Job done. Everything just worked. When you tried multi-party referral, hello, let's all get together and exchange packets, the answer is, well, that ain't going to work. And in some ways, the client-server world said, yeah, it ain't going to work. We're narrowing down the protocol choices, the application model choices to make this scale. But it did.
It did. It happened. It absolutely happened. I remember the moment when the Estonians, who were the people behind Skype, stood up and said, we've made technology which is NAT agile, can find out how many NATs are in the way, and will give you telephone call quality voice and video. It was an amazing moment.
So NATs are brilliant. NATs are literally brilliant. And they've kept the internet going for the next 20 years. And they did it so well. Don't lose your eyes on the global endpoint. We're going to be running V6. This is just a short-term expedience. Everyone's going, meh, short-term, I haven't got a problem. And all of a sudden, the short-term became the long-term answer. And here we are with this mythology that we're still transitioning to V6, but we're not really. Some 36% of the world's, 5 billion users or however many there are, can do V6, but the other 63% cannot. We lost track.
Now, I'm not going to contradict you because I think fundamentally the point you're making here is observably true. The numbers are the numbers. You're part of a measurement activity that's doing end user testing in parallel of your ability to do 4 and 6. You know in the given moment of a user being tested exactly what their capability and preference is. Google do a measurement of the numbers they see. Akamai do a measurement. Cloudflare do a measurement. There's a lot of people out there and the numbers lie in a band of values that pretty much everyone agrees. So ground truth, I think objectively what you're saying is true. It's not happened. It's how we feel about it that I think we might have a bit of drift in this situation, because there are many reasons why it happens or it doesn't happen. And we could actually talk a little bit about that, Geoff, because for some people, moving to 6 has been economically beneficial and transformative.
Well, it's a market. No one's in charge. An individual provider, whether they build host software, mobile phones, or anything else, is going to make this sort of move from V4 only into a dual stacked environment, have V6 as well. They're going to incur that cost in the expectation that they're either going to have more customers, which ultimately leads to more money, or they're going to reduce their cost, which makes better margin, which means more money. And the whole idea of markets are we all as individual players gravitate towards solutions that self-optimize. And this is what the entire transition was all about. The transition to V6 was the risk of address exhaustion is unsupportably horrible. You're all very good risk-averse players out there. God, you started planning for the year 2000 back in 1981 or something. You're all so risk-averse that you're planning forward. V4 is a mess. You're going to do V6. But NATs was so good. NATs was so good that even the actual shock of mobile phones, which forced the internet to scale up by not just a factor of 10, probably not even by a factor of 100. In fact, I think it was almost millionfold. Mobile phones just completely transformed the internet, but they did so without needing V6.
So let's step back and imagine we're CFOs. If my CTO walks into me and said, I've got to make some forward planning on purchase decisions, and I've got a box A, which is Cisco, who say they can sell me this enormous thing called carrier grade NAT, and I have a confirmed price and I know it works, and we stick with what we're doing in every other component of our network, and we just go on doing internet, but I have to run this carrier grade NAT. Or I do what the internet at large community said I should do, which is we have to replace every customer device, every intermediate modem, very possibly some switches. We have to run 2 network stacks. And I have to tell you, it's probably an initial purchase price comparable, but I do think it's better long term. It's probably cheaper, and my TCO might be pretty good out the other side of this. Which one do you want me to do? I know as a CFO what I'm saying. I'm picking the mat.
Well, I would say come back next year when I'm feeling a bit richer. And the answer might be the same next year, but I'm not going to commit. But V6 was a deferrable decision.
Yeah.
And local self-optimization said defer, defer, defer. And while NATs still kept the world alive, there was good sense behind that deferral. And it's produced some pretty odd outcomes. In North America, the impetus for transition has changed.
Yes.
Since 2019, about half, 56% of users in North America have access to V6. The other 44% don't. And the number hasn't changed for over 4 years. The momentum has changed.
The pace of change in America initially looked like a really rapid uptake. And yes, you're right. It maxed out at a number that some might say is 50%, some might say is 65%. And that includes some players who have made a full bore deep dive into a V6 world, who are absolutely committed to providing V6 dual stack, and some providers who simply haven't done anything.
So why did they get it wrong? Why are we able to keep the balls in the air? So I'm going to sort of put a number of things together pretty quickly.
Yeah.
The first is the inexorable pressure of Moore's law. Because when you double capacity every 2 years, computing actually gets per unit cheaper, up to half as expensive for the same unit of computing every 2 years. Storage gets cheaper. And oddly enough, because in fiber communications, the real problem is encoding and decoding the signal. The better your digital signal processes, the more you can stuff down a piece of fiber. And so fiber bandwidth has been inexorably increasing. We're now contemplating 1.6 terabit fiber optic cable systems. If you even went back 10 years and said that, you'd get laughed at. But at the same time, Moore's law is kind of going, yeah, okay, I needed to change my chip from 40 nanometer to 5 nanometer. I needed to bang in an extraordinary number of more processing steps, but I can do it. And I can cheat the price at the same dollar value for that fiber cable. But now I'm doing 10 times the capacity for the same dollar. So we're living in a world where all the parameters of cost of computing, processing, and communications are plummeting.
Have been for the consistent period.
But that's okay. Let's just stay with this.
Under Moore's law. But let's go with this.
Let's stay with this. So has the price of my internet plummeted? Oddly enough, it hasn't. What's happened?
Price and cost are completely disjoint.
Well, oddly enough, though, something even more revolutionary. Because 20 years ago, if I wanted something from Microsoft, my packets went to Seattle, across the Pacific if you're living in Australia. Things were slow, clunky, and really expensive. What did we do with all this abundant capacity and abundant processing and abundant communications? We replicated content, replicated it.
Yeah.
About 90% of all traffic on the internet now comes from a local content distribution network, probably right beside your nose. It's just in your town if you're a big enough town, and moves a couple of kilometers to you. And someone else who's pulling down the same content in a different city is getting it from a different point. It's the same content.
Yeah. In order to get the low latency, high bandwidth delivery that we all crave as consumers, because we have become consumers of mostly unidirectional inflows of large data, putting it local solved the problem.
It made the network faster because we eliminated distance. And because distance is cost, oddly enough, it eliminated a huge element of cost factor. And so by replicating all this content and pushing it out closer and closer to the end user, we actually eliminated the network. Now, let's think about this, because this gets to be a really interesting thought experiment, and we are in that thought world.
We eliminated the necessity for a global network, but there still are cables shipping bits from A to B.
But it's not part of your end-to-end model or mine. We privatized a huge amount of the network.
Right.
Meta run a global network. Last I heard, Google run a whole bunch of cables and have a massively good time. So does Amazon. So does Microsoft. They're not public. They're not running, if you will, in that public space.
Right. We eliminated the public network with you.
Right. We privatized it.
Localize the data, avoid the need for transit, apply Moore's law to get scaling functions that are beneficial to things everywhere cheaply, reduce cost, and eliminate the global network.
I don't need a globally unique IP address for my machine anymore, do I?
Globally, no. You need a unique identity transactionally in the moment of going to somewhere to say, I need to get packets from you. But that somewhere doesn't have a remote care in the world if somewhere else over in Ulaanbaatar receives a request from an entirely different person using the same IP address. You don't need to be globally unique. No.
I don't need to care. And so in some ways, we started to walk away from an address-based network. We walked away. These days, this network runs by names. So the other part of this was, how do you use all this massive abundance? You put all the content into one platform. It's a very big platform, but we can build that cheaply now. And millions of separate web assets, millions of separate service points get loaded up into the one platform with the one IP address. What's the distinguisher? I wanted this thing, not that thing, whatever that thing might be. And the answer is names.
Names. It's the name of the place you think you're going to, the name of the object in that place you think that you're fetching, and your name as a client with permissions to fetch that thing drive all of that process. The actual addresses you use to do it at any given time can be completely mutable 24 hours later.
Right. So now we're in this service environment. We're no longer in a networking environment. The public internet doesn't route. A CDN is adjacent to almost every single access network that exists. I don't need routing security when there is no routing. I'm like, this is just crazy talk. I need the DNS to work, but I really don't care about anything else. The security mechanism that drives today's network is transport layer security. That's it. It's not DNSSEC, and it certainly isn't RPKI. They're irrelevant in today's world. And you sort of go, well, how did this happen? And why did it seem to happen so naturally? Was there a decision point?
No decision point.
And I would actually argue, if you follow the money, you will see why. Because you see, back in the 1980s, moving packets over distance was difficult and expensive, and there wasn't enough capacity. The folk who owned that capacity became the arbiters, became the referees as to who got it, and they used pricing as that rationing signal to access to a scarce resource. So in the 80s internet, it was the communications facilities that cost all the money, and it was the operators of it that got all the money. Yep. The network operators drove the story, and they became our ISPs, and they were still driving the story.
And as a network operator, they would have a network-centric view of the world where addresses are a fundamental construct of networks and network protocols at scale. In that world, addresses were everything.
Right. But Moore's law came along and said, well, I can certainly make communications cheaper. That's good. But I can also make processing and storage cheaper as well. And the whole reason why users are here on the network was to actually do transactions, not just to see the glory of their packets moving around the planet. That was never the endpoint. The endpoint was in service. So what actually happened is, as you shifted from scarcity to abundance in comms and processing, the unit price started to slump, the margin slumped, and all of a sudden it wasn't the money factory.
Yeah.
Google isn't rich by accident. Neither are the social networks. Neither are any of these upper layer service platforms. The money has moved into the application space and left the network. Networking parties aren't fun anymore. There's no money in the room. They're just not.
Well, they've become...
The fun parties are up at the service level.
They've become the utility function that in some ways they perhaps always should have been. Their provision of service represents a public benefit good, a utility, to make packets move along wires. But the component of importance here is not quite the same. It's the things done through that utility function that matter, and we're paying money primarily to the people a layer up the chain. Unless a telco, an ISP, has invested in content, in data center, and in provision of service at that higher level, their margins are thin.
And there was another point too to this computing issue. You see, the other reason why ISPs saw themselves as a critical player was that to get to my users, you need to come through me. I have the billing relationship with all my millions of endpoints. They're there because they pay me. I can provide them with content. I can do billing. I'm the gateway. I'm the tollway. I'm the choke point. Now, all this computing meant a number of things. It meant I can have a relationship with billions of users and not be the network provider. I can do over the top. So the economy of service and content on the network simply moved up because of abundant computing and said, dude, have a really good life, but I don't need you anymore to control access to your users. I'll get everyone to do subscription services, to do advertising content. I can create a whole upper level economy that dwarfs yours. Dwarfs.
Yeah.
So now, inside this new world, and we know what it looks like, we know how it works, let's go back to V6.
Is it net beneficial to me in this new world to be in 6? That is a great question.
No, let's ask an even more brutal question. If I haven't done it yet, who's going to pay me more money to allow me to do it? Will I get more customers if I run dual stack? Well, no.
No.
Will I be able to charge users in my mobile network or access network more if I have V6 as well as V4? No. Who's going to pay me? Nobody. So why should I do it?
You've got a TCO potential, and there are people who argue strongly over the longer lifetime they're demonstrating lower TCO. So future risk management probably led Facebook to an IPv6 preferencing core internal network.
Dear listeners who are living in California and dear listeners who are living up in the sort of Seattle, Vancouver area, there's going to be a big one. And not just a minor shake. When I say big, I mean catastrophically bad. And it's not, centuries away, who cares? Statistically, the San Andreas fault once every 100 years is a big one. The last big one, 1906. Up at the Cascades, there's a big one. And by big, I really mean super, super big. About every 400 years. Last big one, about 450 years ago. I'm sorry, Californians and folk up there in Seattle and Washington, why are you living there?
Yeah.
Because you discount future risk to the point where you kind of go, the weather's nice. Well, not in the case of Seattle. The weather's horrible. For whatever reason, I'm here and I'm okay with this decision, and I'll keep on going there until it all goes horribly wrong. So you're saying this industry does a really good job of assessing future risk. The answer is we humans are horrible at this.
Yes.
If we were really good at future risk, we'd all be vegetarians. We'd all be riding, or actually wouldn't be riding our bicycle. We'd all be walking everywhere.
No, I do hope that your ribs and arm get better soon. We should say at this point that we're all very sorry you had that bike accident, Geoff.
Dear listener, I fell off a bicycle and it hurts badly.
Yep.
But my point is, in some ways, saying a prudent industry would take this future risk into account and move to V6. In an entirely rational world, you are right. In a human world, you're not. And we are living inside this changed world where markets lead and perceptions of risk are much more important than true risk. And so the network we're in now, oddly enough, is a network of names.
Yeah.
Security is now TLS. It's not DNSSEC. It's not RPKI. It's none of that. Interestingly, even routing is now anachronistic. It's now overtaken by events. Because if my content data network has relationships with every single access network, nothing is routed. Everything is simply switched.
There is routing, but it's happening in the interior of that network as a private event that we have no visibility to. It's not
interior of many networks.
Yeah.
So Amazon could be running AppleTalk or DECnet inside their network for all any of us care. Now, the point is kind of their choice and they're in control.
Yeah.
It's not a public facility that needs to be shared and has different targets. And so in this world of the internet is an amalgam of a bunch of private networks and simply a handover at the last mile into access networks that are sort of more conventionally operated as a public service, then the real question is V6 part of this new architecture? And the interesting answer is, well, no. Will it ever be? Well, there's no motivation to get there. There's nothing dragging the market to that outcome. And so in some ways, the American experience where the V6 transition has sputtered to a halt 4 years ago actually says in some ways that perhaps they're slightly ahead of the rest of us. And they've come to an answer that says, well, we've done what we needed to do. We've alleviated some of the acute pressures. Comcast has done its change, and that's great. We can live with what's left indefinitely. There's no point in making any further change.
Now, is that situation equally true globally? I think is an interesting question, because looking at the pace of change, rate of change across different economies, there are many curve shapes here, Geoff. There are economies that have said there's nothing in this for us and they're never going to exceed 5 or 10%. And there are economies who say, well, we ran faster and we've driven to V6 deployment up at 80 or 90%. Compared to America at 60. Is it a competition that matters? The answer probably is no. But if you're a new entrant making a large capital play to deploy new technology basis and you're faced with a choice, there is actually a component of present risk here that to deploy a publicly visible service in V4, you're going to have to buy some addresses. And some people look at that and say, I don't think I want to make that spend when all things considered, starting with nothing, I can pay less to deploy a mostly V6 network with a far smaller bubble of V4. Now, you, of course, are saying the real play here would be to say, I'm going to use any network I feel like, because the only thing that matters is the namespace between me and the content. And as long as they're happy, my addresses are me at that boundary, nothing else matters. Don't think we're quite there yet, Geoff. I think there's still an element of the network there.
George, there's one other element, and we can talk about this the next time, because I think it's also a massive issue flying around with what I call the S word.
Ooh.
Saturation. The mobile phone industry sort of changed the numbers. Everyone now has at least one smart device as well as all the rest of the devices. We've now got a computer on every wrist. We've got stuff in every pocket. At some point, you sort of sit there and go, how far can this go in terms of the current market models? Or is this market saturating? Is there really a conveyor belt of new entrants in the ISP business? No. Is there really a conveyor belt of new entrants in the content distribution network area? No.
Globally, no, but possibly in certain emerging markets, there's still some continued deployment. I could believe Central South America, Africa, parts of Asia, parts of Eastern Europe, there are still significant plays to be made, but it's equally likely they're existing companies, not new companies.
It's equally likely, too, that unless you've got the big five in your data center, in your content network, it's no point doing it. So in some ways, again, this is largely a saturated network.
We're probably looking at consolidation more than increase.
Centrality and saturation sort of go hand in hand. And so these are big theme issues. But the casualty is the 1980s address-based architecture.
Oh, yeah. I don't think there's any doubt at this point that your story is substantively correct. The pressure to deploy to a new world in 6 simply doesn't exist anymore.
So when will this transition end?
Never.
I suspect, dear listener, and certainly I think the answer is there's no reason to actually press on. There's no reason to complete the rest of the work, certainly not economic. It's where we are. It just is what it is. And so this whole, well, we have to do V6 to save the internet? No, it seems to have saved itself in radically, weirdly different ways. We're now a name-based network doing name-based services inside this bizarre privatized, centralized core. And the implications of that is an entirely different conversation about, do these centralists, do the big behemoths, whose interests are they really carrying on with?
Yeah.
Where is this heading and why? But I don't want to depress you too much. We could deal with that another time.
It's been absolutely fascinating, Geoff. Thank you. There's a lot to think about in this.
Thank you, dear listener, for hanging on. And thanks, George. Let's talk about it some more later on. Thanks.
Cheers. If you've got a story or research to share here on Ping, why not get in contact by email to ping@apnic.net or via the APNIC social media channels. Also, remember the measurement at apnic.net mailing list on Orbit is there to discuss and share relevant collaborative opportunities, grants and funding opportunities, jobs and graduate placings, or to seek feedback from the community on your own measurement projects. Be sure to check out the APNIC website for all your resource and community needs. Until next time,